The human visual system has adapted to constraints in the natural environment. The constraints include the fact that many surfaces are earth horizontal, such as grounds and floors, or earth vertical, such as trees and walls. Furthermore, people do not fixate points randomly, but rather choose behaviorally significant points such as objects they are manipulating and surfaces on which they are walking. Because of these constraints, the visual system functions quickly, accurately, and comfortably in the natural environment. But what about VR gaming environments? In this paper, we present measurements of the statistics of eye movements and binocular disparities in VR gaming environments. We then evaluate whether those statistics are compatible with the visual system's various adaptations to the natural environment. An additional user study tested whether observers prefer content that is congruous with the statistics of the natural world and virtual reality. Finally, we discussed the implications for VR headset and game design. Virtual environments, such as video games and VR headsets, may or may not be compatible with the constraints to which the human visual system has adapted. To investigate this, we measured the directions and distances people fixate as people played video games using an HMD that has a binocular eye tracker. And we measured the binocular disparities they encounter in such environments. Capturing the depth buffers of games was required for these measurements. We could not robustly access the internals of commercially available games, so we developed 4 of our own games. These games were representative of popular VR video games. Gaze direction and distance and retinal disparity were computed afterward. The red crosses represent where the eyes are fixating. The gaze data were mapped into the 3D scene reconstructed from the depth buffer images. Then, the 3D scene was projected into the left and right retinas to compute retinal disparities across the visual field. We additionally designed a user experiment in the HMD to directly test whether having seen content consistent with the statistics of the natural environment affects viewer comfort and performance. Participants were shown black text on a white page and asked to read it out loud. There were 2 types of trials, tilt and magnitude. For the tilt trials, the stimulus page was slanted top back in one interval and top forward in the other, having the same slant in each compared pair. For the magnitude trials, the stimulus pages were either both top back or both top forward, but the slants compared within each pair differed. In each trial, participants indicated with a key press which page was more comfortable to read. We also measured how long it took for the participant to read the page in each interval. We now compare results for the natural and the VR gaming environments. The distributions of fixation directions and distances are more restricted in the VR gaming environment, shown on the left, than in the natural environment, shown on the right. And people tend to look much farther in the VR environment. The disparity distribution for the natural environment shown on the right panel has a consistent and prominent property. Near disparities below fixation and far disparities above. That property is less consistent in the VR environment shown on the left panel. The discrepancy between natural and virtual is clearer when we show the differences. From the distribution of fixation distances, we determine how likely it is for vergence accommodation conflicts to occur that are large enough to cause discomfort. In this VR headset, 80% of fixations lead to large conflicts. We computed the screen distance that minimizes such conflicts. Given the distance people tend to fixate, we found the positioning of HMD screens that maximizes the binocular field of view. Shifting the screens nasally creates a generally wider binocular field of view for that fixation distance. The results of the user experiment corroborate our previous finding. Participants preferred a top-back pitch in the tilt trials, as shown on the left panel, and smaller slants in the magnitude trials, as shown on the right panel. Seeing content that violates the top-back pitch pattern of the natural world leads to more discomfort. Participants read the top-back stimuli slightly faster than the top-forward stimuli. This difference was significant, showing that performance is better with content that is consistent with the natural environment than with content that is not. In summary, we measured the directions and distances people fixate in VR gaming environments. The distributions of fixation directions and distances are more restricted in VR environments, and people tend to look much farther in those environments. We measured the distributions of disparity across the visual field in VR environments. The distributions are quite different from one another. One consequence is that double vision is more likely in VR gaming environments. We established that stimuli that are consistent with natural statistics are more comfortable to read and yield better reading performance than stimuli that are inconsistent with natural statistics. From the distribution of fixation distances, we determined how likely large vergence accommodation conflicts are. We computed the screen distance that minimizes the probability of large conflicts and thereby minimizes discomfort. We also found that the optimal placement of the HMD screen is slightly nasal, which differs from the common temporal placement. Please see our paper for more details. Thank you.